Okay, so this is a continuation of the FRQ portion of the Chapter 4 review. This is question 2. This is also a 3-part question, so we're going to be doing this in 3 videos as well. So for question 2, we've been given a table which shows time intervals in seconds, 0, 10, 40, and 60 seconds. It also shows B of t, which is Ben's position here in meters, and we have V of t, which is Ben's velocity, or Ben's speed, in meters per second here, okay? Question A for this one is asking us to use the data in the table to approximate Ben's acceleration at time t equals 5 seconds and to indicate units of measure, and I think that's it. So if we wanted to approximate Ben's acceleration, we would need to move one step further down the line of derivatives. So let's go back one more time to this from question 1. No, not that one. This one here. So if we start at a position, which is a number, which is this one here, the meters, this is just a number of meters. If we want to move to velocity, we have to take a derivative, and that would give us a rate. So this is the derivative of the position. This is the change in position, okay? If we want to go to acceleration, we have to take the derivative of the velocity and get here the rate of change of the rate of change. So this is the second derivative. But we don't have a function. So this is just like the first question, part A, that asked us to find the derivative of our water temperature, even though all we had was the position function. It wanted the rate of change. In this case, we have the position and the rate of change, but they want the rate of change of the rate of change. So we're going to have to do a derivative using this table the same way we did one there. And that is using the function f prime of x is f of b minus f of a over b minus a. This gives us an approximate derivative here, okay? So no matter what type of function we start with, if we use this process, it will give us an approximate derivative of the original function. So if we do this with the position, we'll get an approximate first derivative. We'll get an approximate velocity, but we want acceleration. So if we use the velocity and use this function, we will get an approximate acceleration, a derivative of the velocity. So we have to pick which is going to be b and which is going to be a that will give us the closest estimate possible to what they want. They want the acceleration at time 5. So we need to use the numbers that are closest to time equals 5. So here's t in seconds. We have 0 and 10, and it goes up from there. So we need 0 and 10 because 5 would be right between them. So again, we go chronologically. Whichever number comes first is a, and then whichever time comes next is going to be b. So we're going from 0 to b. So we need to use the equation they gave us. This is going to be v prime of t, because we started with v of t, we're finding v prime of t. We could also call this a of t. This is also acceptable for acceleration. This is going to be v of b, which is v of 10, minus v of a, which is v of 0, over 10 minus 0. Now this is a function of v, so I'm plugging in the number 10 into the function v. I still have to write what I would get out, okay? So if I plug in the number 10, I get out the number 2.3. It's important to look at the v of t function to get the output, not the position function, okay? So I get 2.3. And then if I plug in 0, I get 2.0 over 10. 10 minus 0 is just 10. Now, because this is an FRQ, I can stop right here. I do not have to keep going. If you want to, you can. Just make sure that you simplify correctly. Double check all of your work because you don't want to lose points for a silly mistake when you had the correct answer, okay? If you do want to simplify this, 2.3 minus 2.0 gives you 0.3 divided by 10. If you wanted to go one step further, dividing something by 10 moves the decimal place over by 1, so this is equal to 0.03. But again, you do not have to do these steps. You can stop right here, and your answer is completely correct, so don't worry about that. Okay, So we have approximated his acceleration at time 5, and we got this number, all right? We have to indicate units of measure. We don't have to explain this one, but we do have to indicate units. So we started with meters, and we took a derivative. We added a per second. When we take the derivative again, we have to put in another per second. So up here, this one, this is meters per second, and we divide it by seconds again. So our final answer, no matter what it is, this, or this, is going to be meters per second squared. You can write per second, so you can write meters per second, or you can write meters per second squared. As long as you have 2 seconds and not 2 meters, that will still be correct. You won't have to worry about that. Okay? So that's it for question A. We're going to move to question B in a separate video.